Okay. So the quiz number 3. All right, so to integrate, and then the integral was 3x plus 1 divided by 3x squared minus 4x plus 1 dx. I gave you some options for how to rewrite the integral. So this is similar to an example that I did in the asynchronous lecture when we were talking about completing the square. So first you're going to look at the denominator. And if you're not sure what to do, remember that if you see a numerator that's 1 degree less than the denominator, you should be thinking u substitution, like with a natural log form. You're looking for du over u, but first you have to just make sure that you have that. So what you'll do is you'll let u be the denominator, 3x squared minus 4x plus 1. And then du, you're going to get 6x minus 4 dx. And then you can factor that because you're not looking for 6x, you're looking for 3x. So go ahead and factor a 2 out of that to get the 3x. And then you'll have 3x minus 2. So you'll notice that if you take half du, that gets you to 3x minus 2 dx. This would get you to your u substitution in your natural log form. But you don't have that. You have something really close. So what you're going to do, if you want to create this, you can. You're just going to take your integral and rewrite it by forcing it to be 3x minus 2. But if you subtract 2, you also have to add 2, and you originally had that 1 there. So this is what's going to change. Subtract 2, add 2. And then when you split this up, you can make there be that 3x minus 2 that you want. And then you'll have the additional 2 that you had to add in plus 1, which gets you 3 in the numerator. So these should have shuffled, but yes, that appears to have at least been marked as the correct choice. That's good. So that is the strategic way that you would split that up so that your first integral would be the natural log integral. And then the second one, you would complete the square in the denominator and do that using some sort of probably inverse trig function or trig substitution, most likely. But I didn't ask you to do the whole thing. I just asked you to split it up. Other questions on the quiz?
The one with the trig sub, I guess the second one.
Let's see. All right, so set up the trig substitution. Okay, so number 2. So you have the integral of 5 minus 3x squared to the 3/2 over x dx. So I did one similar to this also during the trig substitution lecture. My suggestion is to write this as a radical so that you have it as in that form that you are looking for your trig substitution. But if you take the square root, then you'll have to cube it because the 3/2 power is just a radical with an index of 2 and an exponent of 3. So that's my suggestion for your rewrite. And then because you're in the form a squared minus u squared, you know that you are going to be looking at u equals a sine theta, and the square root of a squared minus u squared is going to be a cosine theta. So you just need to figure out then what is your value for u and what is your value for a. So if you have under your radical 5 minus 3x squared, well, 5 is going to be the square root of 5 squared, and then minus, and then for u, you're taking the square root of 3 times x and squaring that. So you're getting a is equal to the square root of 5, and u is equal to the square root of 3 times x. So each one of those quantities needs to be rewritten as a square. So when you fill this in, you're going to have the square root of 3x equals a, which is the square root of 5, sine theta. And then your a squared minus u squared is going to be the square root of 5 cosine theta. I hope this showed up right. Yeah, this one I had to rewrite so many times. I was getting very frustrated with it. Let's see, square root of 3x. It kept showing up without one of my options and just deleted it every time. It never happened to me before until last week. So this is your setup for number 2. Seemed like the actual integration for number 1, it sounds like, was better. Does anyone have a question on that one, or are we okay with that?
I think that was easier.
Okay.
It was pretty straightforward.
Okay. Okay. Wonderful. So today I have to finish out 7.4, which was integrals involving the form ax squared plus bx plus c. And then I'm going to start some partial fractions in 7.5, which are going to look kind of similar to the integrals in 7.3 and 7.4, except they're going to have one major distinct difference. So we'll do that. Oh, I was just about to do this when I realized you were done with your quiz, and I had to pop back on. I was just kind of seeing where we are schedule-wise. There we go. So I think I'm technically supposed to be finishing 7.5 tonight, and I just don't know if I'm going to be able to get all of it done. I don't think I will. So, I mean, how are we doing? I can't see any of you, so I don't have like a Pear Deck or anything set up to do like a, how are we doing?
I'm doing better this chapter than last.
Okay. Alberto, go ahead. Did you raise your hand? Who raised their hand?
I raised it by accident.
Oh, you changed your mind.
Yeah.
Okay. Oh, you didn't change your mind. You just didn't mean to. Okay. Because I can't tell, and from the homework, a lot of us haven't gotten very far, which is somewhat concerning, but I mean, not all of it was due. I mean, if I'm looking at trig integrals, I mean, it looks like the people who did it did okay. There's a lot of did not start on here. Oh, some of these people aren't even in the class anymore. I should remove them.
Yeah, I'm feeling like I'm grasping this chapter a lot better than the previous chapter. I'm just having some issues with entering it and to achieve.
Yeah, I know. Achieve is kind of a bear that way. Sometimes it's fine, and then other times I don't know, the templates are a little funnier. Because I guess I'm kind of thinking like maybe I should just finish the asynchronous on 7.5 and then just kind of build in a little bit of buffer time. on some of this other stuff. Just, I don't know, to give everybody a chance to make sure that we've got all these integrals together. I think your book actually has like a, let me double check this, like a synthesis kind of section, but it might actually have instead something at the beginning and not at the end. Because if it had something like synthesis, then I would do that. But 7-9, I think. Yeah, 7-9. What I might do, and actually this is what I think I'm going to do. Okay, so here's the deal. Once I finish out 7-4 tonight and 7-5 asynchronously, that's pretty much what you're going to be doing as far as special by hand integration techniques. Now 7-6 is like a kind of a departure. You're doing lots of like estimating and approximation. So not the same as actually doing techniques. You're going to be applying formulas, but I mean, I think for the most part, that's pretty straightforward in 7-6. Then we have to go back to 4.5, which I know seems like it was a Calc 1 topic, but if you took Calc 1 at ECC, then you did not have 4.5 in your Calc 1 class. It's L'Hopital's rule. If you took Calc 1 in high school, you probably had it before. So if you took Calc 1 in high school, you've seen L'Hopital's rule, not that big of a deal. We do have to do that before we do 7-7, which is improper integrals. And then still, that's not like integration techniques like we did in 7-1, 7-2, 7-3, 7-4, 7-5. And then 7-8, we're just going to be talking about using tables. So I think once we finish these major technique sections, 7-1 through 7-5, maybe I'll just have you guys work on 7-9, which is pulling it together. And then maybe I'll even have that homework due, like I'll give you a little bit of extra time so it's due before the test. You don't have to do it right away, but maybe just to get started, just understanding the differences between these types of integrals and pulling them all together and knowing what to do when, knowing when to complete the square, when to use partial fractions, knowing when you're looking at a trig sub versus like an inverse trig function, knowing when you have to use parts. So the 7-9 isn't really anything that I teach to you. It's in your book, but it's not a new lesson. It's called mixed practice. So I might just throw that in after 7-5, and then that will kind of give you some time to pull things together.
I think that would be good.
No.
Okay.
Person opened the door was.
Yeah, and then we can sort of move on with the rest of the chapter, which is a little bit different. Yeah, so maybe I'll just do that. Okay, so tentatively we'll plan on that, but I will of course let you know via email whenever I upload your asynchronous lecture. So maybe we'll just make that video a little bit shorter to give you guys some catch-up time, because I know there's a lot, especially when you're sitting there thinking like, okay, how do I start? And that's always the hard part with integration is it's not like taking a derivative where you're looking at it and you just kind of start going with the chain rule or with the product and quotient rules. With integration, a lot of times you look at the problem and you just kind of stare at it. And yeah, if you're in the integration by parts section, then yeah, of course you know that you're supposed to use integration by parts. But if you're not in that section, then sometimes it's hard to know. So on a test, I'm not going to say use integration by parts, use trig substitution, complete the square, use partial fractions. You're going to need to know when to do that. And that's kind of where 7-9 comes in, with just looking at different types of problems and getting a good idea of what to do when you see certain things. So like I said, yeah, if you're in trig sub, you know you're using a trig sub. But if you're not there, then how would you know? It's really just about practicing and seeing different things. Okay. So that being said, that's kind of what I'm thinking right now as far as structuring this a little bit differently. All right, so in 7.4, I left off asynchronously with you guys after example 3. And then I said I had 3 more examples I was going to finish with you today. So I'm going to start out doing that. Okay, so this is 7.4. Continued. And 7.4 is kind of nice too, even though 7.4 itself is not like a let's pull this together mixed practice. In a way it kind of is, because these sections all kind of build on each other. So every once in a while you'll see a question in like 7.3 or 7.4 that uses integration by parts, for instance. So once you learn something, you might see it again mixed in with another topic. So we're going to be doing a little bit more of that here. Example 4, we're going to do another definite integral. So this will be the integral from 1 to 4. And I'm going to give you a fraction here. In the numerator, you have x squared plus 4x minus 5. And in the denominator, you have x plus 2 dx. So what we've been doing in this section is completing the square. And we're going to do that again here. And if you weren't sure what to do, you'd be like, where do I start? Well, especially because your trinomial's in the numerator and not the denominator, there's really not a whole lot for you to do here except complete the square. It's not like you'd be going for some sort of, would-be u substitution. This doesn't even fit the form for an inverse trig function because, first of all, your radical would have to be in the denominator. And even if it was, you would still have to complete the square to get it into some variation of a squared and u squared. So let's complete the square here under the radical, and then we'll put this back together again. And I am trying to give you a little guidance as we go through here as to like, how do you know what to do? Like if you just saw this problem out of the blue, how would you know how to approach it? It's hard to really teach that. I mean, I can show you a lot of different examples and a lot of different things, but really it's just about you practicing and doing it yourself. That's really where you're going to learn. Okay, so to complete the square here, I want to make sure that my constant term is half of the middle term's coefficient squared. So half of 4 is 2, square that and you get 4. Add that in to complete the square. Since you added it, we also have to subtract it. So here's your perfect square trinomial. And we'll rewrite that as x plus 2 quantity squared. Hopefully we're getting pretty good now at completing the square since we've done so much of it. And then add in those last 2 constants to get your minus 9. And then we're going to put this back into our radical. So we're just going to rewrite the numerator as the square root of x plus 2 quantity squared minus 9, and then we'll divide by x plus 2 in the denominator. Okay, now once you complete the square, then I feel like things start to become more obvious. So we're getting moving now where you can start to see like, okay, I have some quantity squared minus another quantity squared. And then you should be thinking trig substitution at that point. Like I said, we're not in the form of an inverse trig function because I would need this in the denominator. The x plus 2 is causing us problems. We don't want it there. So this is really the only thing you can do at this point is do a trig sub. So for your trig substitution, we are going to let u be this squared portion. We're going to say u equals x plus 2, that's the quantity being squared, and then a equals 3, that's the constant that's being squared to get a squared, which is 9. And then you need to recognize which form you're in. So in this case, when you take u squared minus a squared, well, we're going to let u in that case be a secant theta. And then we're going to let our radical, the square root of u squared minus a squared, be a tangent theta. And now we'll start to sub everything back in. So we have x plus 2 as 3 secant theta. And remember, whenever you're looking at x, you also want to find a dx. So right now you have an x plus 2. We're going to substitute that directly in. So we don't actually have to have just x in this case, but we do need just x for our dx. So we'll have x is 3 secant theta minus 2. And then dx, well, the derivative of secant u is secant u tangent u. So we'll have 3 secant theta tangent theta d theta. Now for your square root, for u squared minus a squared, we will have a, which is 3, and then tangent theta. Okay, let's go ahead and sub this back in. We do have a definite integral, and we're going to have some options here as to what we want to do with that. But for right now, I don't want the limits of integration to disappear just because I don't want to forget about them and end up solving this as an indefinite integral. So I'm going to go ahead and mark them as x equals 1 and x equals 4 so they don't end up representing theta in our integral. I want to make sure that we remember which variable is which. All right, so our radical is 3 tangent theta. And then x plus 2 is going to be 3 secant theta. And then dx is 3 secant theta tangent theta d theta. If you guys have questions, please don't be shy. If you want to use the raise hand feature, or no one, it's not like I have a class of people that are all just speaking up at the same time, so it's fine if you pop in with a question.
Are we gonna change our bounds instead of leaving them at x?
We're gonna have to switch something eventually. I just wanted to sub out the integral first and simplify that, and then we'll kind of revisit that and figure out what we want to do with them. So right now I just wanted to do the substitution for our x variable as far as the trig functions are concerned.
Okay, I'm sorry if but I kind of missed where you got the like x plus 2 squared minus 9 from the original problem. Can you just go over that real quick?
Oh yeah, so we started out with this quantity, right? And then you take, to complete the square, you take half of the middle term, which is 4. I'm sorry, half of 4 is 2. And when you square 2, you get 4. And you add that on, and then you create this perfect square trinomial. But if you're going to add in 4, you have to also subtract 4.
Okay, I remember doing this, yeah. All right.
Okay. Yeah, so once you have your perfect square trinomial, factor it, and then just write your constant. And then you'll have in this case, difference of 2 squares. I'm glad you asked. Other questions? All right, so let's go ahead and simplify a little bit here. I can get rid of an entire 3 secant theta. And then what I have left here is going to be the integral from x equals 1 to x equals 4 of 3. I still have this 3 from the numerator, and then tangent squared theta d theta. Okay, so our options here are we can rewrite the limits of integration, or you can back substitute back into X and then use your original limits. I feel like there's so much substitution going on here that students tend to get more confused when I switch these. So I'm probably just going to back substitute and keep my original X limits. I know that's not usually what we do in Calc 1. The main reason I force you to do this in Calc 1 and switch your limits is because your Calc 2 teacher is usually doing that. And I want you to know what your Calc 2 teacher is doing when they do that. And if you'd like, stick around for the office hour and we'll switch you over to theta limits. But I personally have found that students get more confused when I switch these, especially with the trig substitution where there's so much going on. So I'm going to keep these original limits and I'm going to integrate and back substitute to X to evaluate them. That's my plan. But that's up to you. And you're going to be working on the same process regardless. So whether you back substitute or change them now, you're going to be doing the same math to get there. All right, so tangent squared, I can't think of a function whose derivative is tangent squared, but I know that the derivative of tangent is secant squared. So if I can get this written as a secant squared, then I'll be able to solve this integral easily. This is actually a Calc 1 integral, even though it doesn't look like it. So I'm going to rewrite this. Again, I'm keeping the X equals on these so I don't forget that they're X limits. So that's one thing I'm going to ask you to do if you're going to back substitute in the end. Don't just say 1 to 4 because that implies it's theta, not X. All right, so I'm going to rewrite this. If I know that tan squared plus 1 is secant squared, then I know that I can rewrite tangent squared as secant squared theta minus 1 d theta. And then I can integrate because I know that the derivative of tangent theta is secant squared theta. So I'm going to say that this is 3 times, and this is going to be tangent theta minus theta, and that goes from x equals 1 to x equals 4. And, you know, double check, make sure that you do end up getting this back as your derivative. Derivative of tangent is secant squared. The derivative of theta in this case would be 1. All right, now I'm going to rewrite the thetas back into x's so that I can evaluate this definite integral. Before I do that, are there any questions here?
Nope.
All right, so let's see. I'm going to go back and find tangent theta and theta. So I have right here tangent theta. I'm going to take my radical and divide it by 3 to get to tangent theta. Now, if you want to rewrite it like this, fine. If you want to keep it in its original form, that's fine too. I might even just do that because it's slightly easier to write. They are equivalent. Just one of them has the square completed, the other is in a different form. So you can say that tangent theta is your radical divided by 3. And then just as far as theta is concerned, you can take this back the opposite direction. And we can say that x plus 2 divided by 3 is equal to secant theta. And then we can solve for theta by taking the inverse secant. Of x plus 2 over 3. So now we have tangent theta and theta. I'm going to back out a little bit. If you want to leave the 3 factored out, you can. If you want to multiply it in, that's also fine. Up to you. Tangent theta is the square root of x squared plus 4x minus 5 divided by 3. And then theta is the inverse secant of x plus 2 over 3. And then we're taking that from x equals 1 to x equals 4. And it could be that now that you're seeing it in this form, where you have a 3 in the numerator and a 3 in the denominator, and you want to cancel it, that's fine. Remember that you can't cancel these because this denominator 3 for your inverse secant is actually inside the inverse secant function. So I'm going to just go ahead and distribute the 3 just so I have fewer grouping symbols to worry about. So my first term is just going to be the square root of x squared plus 4x minus 5. If you want to leave it as the squared version, if you did that, that's fine too. Actually, that would be easier to evaluate. You know what? I'm already rethinking this. If this was indefinite, I probably would leave it, but I might switch it back because it's going to be easier to evaluate this if it's written as the difference of two squared functions. So I'm going to switch mine back here. I actually don't mind that that happened because I think we need to get comfortable being able to work our way back and forth between these forms. And then we'll say this is minus 3 times the inverse secant of x plus 2 over 3. And then we'll go from 1 to 4. And now that we're in the same variable, we don't need to keep writing x equals. It's assumed at this point. As long as the variables match, I can just simplify my notation. So I have the square root of 4 plus 2, which is 6 squared, minus 9, minus 3, times the inverse secant. Well, 4 plus 2 is 6, divided by 3 is 2. And then I'll subtract off the evaluation at the lower limit. So when x is 1, I have the square root of 1 plus 2, which is 3 squared is 9. 9 minus 9 is going to get me to 0. And then minus 3 times the inverse secant of 3 over 3, which is the inverse secant of 1. And then you're just going to have to think about your inverse secant. Okay, questions here? We good? Okay, 36 minus 9 is 27. You're asking yourself here for the inverse secant of 2. You're looking for theta such that the secant of theta equals 2. That means that you're looking for where the cosine of theta equals a half. So you're going to find that it's probably a lot easier to think about this in terms of cosine. Pop this down a little bit. So I know that the cosine of pi over 3 is a half. So I'm going to bring down my 3. And the inverse secant of 2 is going to be pi over 3. And then we have minus 0 plus 3 times the inverse secant of 1. Well, again, you're looking for an angle such that the secant of theta is 1. That also means the cosine of theta is 1 over 1, which is 1. The cosine of theta is 1 when theta is 0. So the cosine of 0 is 1. So your theta is 0. the square root of 27, break that down into 3 times 9. 9 is a perfect square. Simplify that to the square root of 9, which is 3, and you still have 3 left over. And then 3 times pi over 3 is pi. All right, questions on example 4? So there's a lot going on here. We started off noticing that we had a trinomial in the form ax squared plus bx plus c. Weren't quite sure what to do with it. It was not already a perfect square. If it was already a perfect square, we could have square rooted it and then just simplified it that way, but it wasn't. So we turned it into u squared minus a squared, and then we set up a trig substitution using the values that correspond with the square root of u squared minus a squared. Then we subbed it out, integrated, back substituted for x, and then we went back and got these definitions to back substitute for x, and then we evaluated at the original x limits. Okay. Wonderful. The next one I would like to do is continually getting lost in my notes. Here it is. Zoom you back in. Example 5. This is the integral of x squared divided by the square root of 2x minus x squared dx. I know that I did one like this, and I'm trying to figure out if it was in this section. I just wanted to remind you. Oh, it was example 3. It wasn't just like this. It was kind of similar to this just because of the setup of the trinomial. Technically, it's not a trinomial, but the constant in this case is 0, but it's still in the form ax squared plus bx plus c because a is equal to -1. It's not 0. So this is another one where you're originally looking at it and you're thinking, I don't know, maybe let u be the denominator. But if you did that, if you let u be not really the denominator, in this case, it'd be the radicand, you would get du is -2x plus 2. And you wouldn't be able to come up with this x squared. So you'd have a lot of issues here trying to do a u substitution with this, and you'd probably get stuck. Then you'd say, okay, great, what am I supposed to do to solve this integral? By the way, ECC every year, I don't think they're doing it now because of COVID. They might do it this semester since they're in-person classes, but I haven't heard anything about it. But every year, twice a year, they have something called an integration contest. And you're eligible to be in the contest if you've at least if you're in Calc 2 or above. And basically, it's just that you sit in this room, and it's like an elimination style thing where everybody gets an integral to work on, and you have a set amount of time to do it, and you see if you can finish it. And then basically, like, people just start dropping out because they can't finish it or they didn't get it right. But it ends up being very interesting at the end because there'll be like 2 people left and they're like fighting to the death. But anyway, if they have it, I'm going to make sure that I get you guys all the information. But there's a reason there's an integration contest. It's because integration is tricky, and you have to know what to do when you're looking at an integral. So, just keep that in mind. Half the battle is just in getting some sort of a game plan. So we're going to complete the square here. And if you're wondering, how can we possibly complete the square? We don't really have a trinomial to work with. We still have something where we can complete the square. So let's go ahead and take this quadratic expression out of your radical. I'm going to take it out directly like this. Now, like I said, we did something similar to this in example 3. The difference was in example 3, we had a constant term, but we had a similar setup. Actually, the one in example 3 was slightly harder because we had a coefficient that was like negative. Looking for it now. It's like negative 2x squared. And then we had to factor it out. At least we don't have that situation. All right, so rewrite this so that it's in descending order. And then you're going to factor out the negative. When you complete the square, you don't want that negative in there. So factor out the negative, and then you can write this as x squared and then minus 2x. Make sure you factor it out of both terms. Now you're going to complete the square inside the parentheses. So act like the parentheses and the negative sign aren't there. Just focus on the x squared minus 2x, and we're going to complete the square in there. So half of 2 is 1. 1 squared is 1. So we're going to add 1 to our expression. And this is where you need to be really careful, because even though it looks like you added 1, remember that this negative sign is going to get distributed. So you actually subtracted 1. If you subtracted 1, you also need to add 1. So be very careful here to make sure if you were to distribute, you'd get negative x squared plus 2x minus 1 plus 1. You'd end up getting back where you started. That's what you want. Complete the square inside your parentheses. And remember, you're looking for this to be in the form a squared minus u squared minus a squared, or a squared plus u squared. The way you're going to make that happen is to switch the order of subtraction. Make the negative term second. Now, you'll know that you did this wrong if both of these terms are negative, because we don't have a form for negative a squared minus u squared. So if you ended up accidentally subtracting 1 here, because maybe you're like, all right, I added 1, let me subtract 1, then this would have become a minus, and then you wouldn't have known what to do. You'd be like, I don't know, like factor a 1 out, and then you'd put a 1 in front of your integral, and weird things would happen. You shouldn't see that happen. You should get these signs to be opposite in this particular case. Questions on the completing the square? Okay. Now I'm going to put this back into the example. The numerator is not going to change. The denominator will be the square root of 1 minus x minus 1 quantity squared, and then dx. Okay, so sometimes it's just about doing some algebra work, and completing the square is just algebra. And once you get down to here, I feel like it's much more straightforward. Now you have an idea of what to do, because now you're noticing that you're in the form a squared minus u squared, where a is equal to 1 and u is equal to x minus 1. When you are in the form a squared minus u squared, your trig substitution is going to be, we're going to let u be a sine theta, and the square root of a squared minus u squared is a cosine theta. So x minus 1 is going to be equal to 1 sine theta. And we do actually need an x squared in this case, but we're going to need x anyway just to get dx. X is equal to sine theta minus 1 dx is equal to cosine theta d theta.
Didn't you want to say +1?
Oh, yes, +1, sorry. That would have been a little tiny small thing that would have screwed up my whole problem, right? Thanks, Becky. Okay. And now for your quantity, 1 minus x minus 1 squared, you're going to get 1 cosine theta, or just cosine theta. And now we can start to sub everything back into our integral. Before I do that, are there any questions on the substitution? I don't want to make this too small for you guys to see, but sometimes I think it's helpful if you can see more of the early part of the problem because we do refer back to it. All right, so x is equal to sine theta plus 1. We're going to square it. And then that is getting divided by cosine theta. And then dx is cosine theta d theta. So we have x squared divided by your radical, and then you've got your dx in here as well. Okay, now it's probably screaming out to you to cancel out these cosine thetas. I absolutely agree. So now we have sine theta plus 1 quantity squared d theta. I would not try to use a u substitution here because if you did, u would be sine theta plus 1 and du would be cosine theta d theta, which you don't have. So you're going to want to expand this out by squaring it. And I'm even going to show you the squared form because I know that we've had a bad history in this class of distributing the exponent. So we're going to rewrite this as sine theta plus 1 times sine theta plus 1 d theta. When you square it, you're actually going to FOIL out that quantity. And now we'll rewrite the integrand as sine squared theta, and then plus 2 sine theta plus 1 d theta. We talked when we were looking at 7.2 about what to do when you have something in your integrand like sine squared theta or cosine squared theta. We use power reducing formulas to get these down to functions that were more easily dealt with. Recall, I know you probably used it so much on the homework, so it's very fresh in your mind, but sine squared theta is 1/2 times 1 minus cosine 2 theta. And then we'll just have to deal with that multiple angle when we get there. So I'm going to split this up. 1/2 times the integral of 1 minus cosine 2 theta d theta. And then the other two terms, if you want, we can just integrate right here and now. The derivative of cosine is negative sine. Well, you have positive sine, so you're going to have minus 2 cosine theta plus theta. If you want to pop on a plus c, fine. We just now have to deal with this part of the integral. But the other two terms are done. So you're going to have 1/2 times theta, and then the derivative of sine theta is cosine theta, so minus 1/2 sine 2 theta. then you can just pull down the rest of this. And I'm going to simplify this a little bit more. Just, I don't want to look at all these grouping symbols. Before I do that, does anyone have a question here? Wonderful. So we have 1/2 theta minus 1/4 sine 2 theta. Now, some of you guys ran into some issues on the homework with these multiple angles. We're going to rewrite this using our double angle formula for sine. Oh, and you know what? You might want to combine those two thetas in a second too. So I want to do another recall. Sine 2 theta is 2 sine theta cosine theta. So we're going to sub that out as well. So that means if you have 1/4 sine 2 theta, then you'll have 1/2 sine theta cosine theta. So just divide both sides of the equation by 4. All right, so notice you have these two thetas that you can combine together. You have 1/2 theta plus 1 theta, that's 3/2 theta. And then we have minus 1/2 sine theta cosine theta minus 2 cosine theta plus c. Now we need a sine theta, a cosine theta, and a theta. Well, we have sine theta and cosine theta that we already put together using the information from our trig substitution way back when. I don't even know if I can get it on there. No. All right, so sine theta is x minus 1 right here. Cosine theta is our radical. You might find it's a lot easier, especially since we don't have a definite integral, we have an indefinite integral. You might find that it's a lot easier just to rewrite this in its original form, which was the square root of 2x minus x squared. So I'm probably just going to write mine like this, just because it looks slightly more simplified than that, but they're the same thing. So you decide between these two forms which one you want to use. Okay. Oh, and we need a theta. Sorry, I almost forgot about that. If we already have this information, then we can say that theta is the inverse sine of x minus 1. So take the inverse sine of both sides to get theta by itself. Okay. So we're going to have 3/2. We said theta was the inverse sine of x minus 1. Sine theta is x minus 1. Cosine theta is the square root. I'm going to leave mine in its original form of 2x minus x squared. And then minus 2 cosine theta plus c. Now, I'm not going to be crazy picky about making you multiply this in and having an x term and then like a 1 times this quantity. This is fine. Leave it like this, stick a fork in it, it's done. Okay. I do have one more example, but if you have questions on this one, think on it for a moment. I'll give you a minute here to think about it. You know, sometimes it just takes a minute just to catch up. Trying to see now how many people actually got through the 7-4 homework. Okay, nobody. That's fine. It's not due till Monday anyway. At least nothing was submitted. I did assign it, right? Oh, there we go.
The homework, yeah, the 7-4, yeah.
Excellent. Okay, so example 6, there are a couple of problems on the example or on the 7-4 homework that are similar to example 6. And example 6 is similar to example 3, which was the last one I did in your asynchronous lecture. Wait, no, it wasn't example 3, it was example 2. Yes. So example 6, which I'm about to do, is very similar to what we did in example 2 in this section, which is also very similar to quiz question number 3, which you guys asked me about at the beginning of class. I had said that I had one of these for you. I don't know if you remember, and you were excitedly waiting and with, you know, anticipation, but it's here now. Before I take away example 5, does anyone have a question on it? Okay, so, you know, the problem here, I mean, nothing here that we did step by step was really that hard. It's just that there are so many little things that you have to put together here. Just with even just completing the square, making sure that you know how to integrate this using 7-2, because this is a 7-2 problem here, being able to reduce the power down. I mean, technically you learned it in trig, but we applied this in 7-2, and then just working backwards and using your trig formulas here to back substitute. So it wasn't like one single step was all that hard. It's really just being able to put all of this together and kind of have a roadmap for where you want to be. Example 6. I really like these examples. This is the integral of x plus 3 divided by the square root of x squared plus 2x plus 2 dx. Now, this looks kind of similar to what we did in example 5, looking back now, and kind of similar to what we did in example 4. However, you're going to need a different approach for this one, and I'm going to show you why. Mostly, I just need for you to understand when this approach is necessary, and that's a hard thing to teach. I don't want to go off on half a page of don't do this. And that's really what I would be doing here if I started this out with a normal trig substitution. Now, I would think that before you guys ever started a trig substitution, hopefully you would check first to see if you were in the form of a natural log. So I'm looking back at what we did in example 4 and example 5. Now, when I started out example 4, I said there's no way you can be in the form of a natural log function or any sort of u substitution because of the fact that if you let your u be in the numerator, your du would be in the denominator, which you don't want. So if these were switched, you'd have a situation that was similar to example 6 with your radicand in the denominator and your linear function in the numerator. But because they're not, and you have the radical in the numerator, for example 4, that's sort of keying you into like this can't be a u substitution. It has to be a trig sub problem. Now, for example 6, you might try a u substitution first because it's possible that it could be a u substitution. For example 5, you have that radical in the denominator, but we talked about the possibility of it being a u substitution, and we said that if you tried that with example 5, you'd end up in hot water because your du has the same degree as your numerator has the same degree as your radicand. So right off the bat, you can't have a situation where you have the square root of u du, where the square root of u is in the denominator. So that's kind of the difference between 4, 5, and 6. And that's why we have section 7.4. You're understanding the differences between these examples. Here you have the radical in the numerator. That's telling you right away, this has got to be a trig substitution, most likely. When you have your radical in the denominator, if the degrees are the same, then you're probably not going to have a u substitution because you want your du to be in there, and to have a derivative, you need the degree to be 1 less. This is a situation where I'd go for a u substitution. Example 6. This also brings me back to quiz question number 3. Okay. So if you were going to try for a u substitution, you would let u be your denominator. Or I'm sorry, the radicand in your denominator, not the entire denominator itself. And then you would say that du is 2x plus 2 dx. Well, you don't have 2x, you just have 1x. But you can kind of see where this is going now. Divide both sides by 2, and you'll get x plus 1 dx. You're going to have to split up this function because part of it is going to work with your u substitution, and there's going to be extra stuff in here. You're going to have an extra couple of terms, or at least an extra term that is not going to work with your u substitution. Now, sometimes you might be able to work your way through here and just do a trig substitution. If you would like to stick around for the office hour, we can look at the case where you just try to do a trig substitution. I did try to do it already. You end up in a situation where you have an integral that you don't know how to solve. And if that seems weird, like why would that be the case? It's because you're going to end up having extra terms here if you do a trig substitution. What we're going to do is we're going to lend this x out to the u substitution. And our trig substitution then is just going to have a constant in the numerator. So what we're looking for is a situation where we're going to have 1/2 du is x plus 1 dx. That means I need to create this in the numerator. Well, I don't actually have that. I have x plus 3. So what we're going to do is we're going to rewrite x plus 3 as x plus 1 plus 2. And the x plus 1 portion is going to be part of a u substitution integral. The portion that has 2 in the numerator is going to be part of our trig substitution. So I don't want you to think, oh my gosh, how would I ever know how to do this? You're specifically seeing this on a couple different types of examples. And if I can remind you of what we did, if I can find it in example 3, it's right here. No, example 2. I keep saying 3, but it was example 2. We actually did something similar in example 2. This was asynchronous, but it was still part of 7.4. Notice that you have the same situation here. You just don't have the radical. So you had a trinomial and then you tried to create the u substitution, we found that if we had 3x plus 9, we'd have the u substitution. But we didn't have 3x plus 9. We just had 3x. So we forced there to be a 3x plus 9, and then we subtracted off the 9 that we created. So we used part of it for a u substitution, and part of it we turned into an inverse trig integral. We could have probably done this. Oh, I think I said it at the time. We could have done this probably with a trig substitution also. Yes, we could have, but we did not. So that's another thing. If you want to stick around for the office hour and do example 2 using a trig substitution, we can do that. I only have so much time in this class, but you do have some options here. So I don't want you to think that example 2 and example 6 are really that different. They're not. This one just is going to look more like a trig sub, whereas this one you were able to do a little bit more with it as far as your inverse tangent form was concerned. Okay, so that's sort of walking you down memory lane for your asynchronous lecture. I was just thinking, most of you probably watched it at this point. I don't know, it has more views than I have students, but if you did not watch it, you're going to be really confused right now, wondering like, what is she doing? I've never seen this before. That's why it's really important to watch your asynchronous lectures before you come back again. All right, without further ado, let's rewrite this. So I'm going to split up my integral. I'm going to have x plus 1 divided by the square root of x squared plus 2x plus 2 dx. And then I'm going to have plus twice the integral. If you want to put the 2 in the numerator, you can. If you don't want to, that's fine. Of dx divided by the square root of x squared plus 2x plus 2. You know what? Just because I'm splitting it up, I'm going to put my 2 in the numerator. So it's really clear that nothing has really changed. I'm going to move it in a minute. Okay. So x plus 1 plus 2 is x plus 3. This is going to be your u substitution. This we're going to use with inverse trig. Now, you had more options on example 2 because we did it using an inverse trig derivative. Sorry, I meant to say trig substitution. Gosh, I do this every time. Trig substitution. With example 2, we could have done trig sub, or we could have done an inverse trig function. We did an inverse trig function. This one, you're going to be forced to do a trig substitution. If you're not sure why, I'm going to show you why. In order to do a trig substitution, we're going to have to complete the square. Before I do that, does anyone have questions on the setup so far? All right, x squared plus 2x plus 2. I am going to complete the square. Half of 2 is 1. Square it, and you get 1. If you add in a 1, you need to subtract off a 1. Now, complete the square by factoring and subtracting 1, rewriting your constant term. Okay, now since this is going to be under a radical, it's not an inverse trig form. An inverse trig form is du over a squared plus u squared, but it doesn't have a radical in it. Your other two inverse trig forms do have radicals. They're du over the square root of a squared minus u squared, and they're du over u times the square root of u squared minus a squared. The inverse tangent integral doesn't have a radical. So this is going to have to be done at this point using a trig substitution. You don't have a choice to use an inverse trig function. All right, so we're going to rewrite this. I know it's a lot of rewriting, but we want to keep everything organized. So I'm going to write 2 times the integral of dx divided by the square root of x plus 1 quantity squared plus 1. Now, if you're wondering, why did she write it as a sum of two squares in the second integral, but not the first? Well, I don't need to rewrite it in the first integral because I'm just doing a u substitution. So you can if you want to, but you certainly don't need to. If anything, I think it'll throw you off more because you'll think you're supposed to do something. You'll think that you're supposed to do something different with it. And you'll get confused. Okay. Now it's up to you how you want to note this. If you want to go ahead and evaluate the first integral and then the second, that's fine. I find that trying to do these two simultaneously is like really, really messy and confusing. So I work on one of them at a time. And this one is first, so we might as well just do the u substitution first. And then we'll do the trig substitution. All right, so this is your u substitution. You actually already did the work for this. Zoom you out a little bit. So the work for your u substitution is up here. I know that 1/2 du is x plus 1 dx. So I can rewrite this as 1/2 times the integral of du divided by the square root of u. And if you would prefer to write it, I'll leave it like this for now. We'll rewrite it again anyway. So the 1/2 du is x plus 1 dx, and then the square root of u is what's in your denominator. So this is a Calc 1 integral right here. And in Calc 1, when you saw these, you rewrote them, for instance, as u to the negative 1/2 du. The square root gives you the 1/2 power because it's in the denominator, it's negative 1/2. You're going to add 1 to the exponent and divide by the new exponent. So when you add 1, you get up to u to the positive half. And then you're going to divide by your new exponent, which is 1/2. And when you divide by 1/2, you multiply by 2. 1/2 times 2 is going to give you 1. Or you can just think about this as 1/2 divided by 1/2 if you want to do it that way too. But either way, you just get the square root of u. And then you can sub that back and say that this is the square root of x squared plus 2x plus 2 plus c. So this is a preliminary result. It's part of your answer. But now we have to work on the second term. All right, questions on the first term integral? Okay. All right, for the second term integral, we are gonna, if you want, you can remember the 2 at the end. I'm just gonna keep it on there so we don't forget about it. We're looking at twice the integral of dx divided by the square root of x plus 1 quantity squared plus 1. We're in the form u squared plus a squared. So u is going to be x plus 1, and a is going to be 1. When we are in this form, we let u be a tan theta, and the square root of u squared plus a squared is a secant theta. So we have x plus 1 equals tangent theta, and the square root of x plus 1 quantity squared plus 1 is secant theta. don't forget that you're also going to need a dx. So x is tan theta minus 1. The derivative of tangent theta is secant squared theta. The derivative of 1 is 0. Okay, that's your setup for your trig substitution. Questions there? All right, we've still got this 2 in front of the integral, the constant multiple. I'm just going to bring that down. Dx is secant squared theta d theta. And then in the denominator, I just have secant theta. I'm really trying to assign homework problems. I actually painstakingly went through every single one in 7.3. One of them ended up not matching, and then I got super irritated with it. But I wanted to make sure that you weren't going to end up with something crazy. A lot of integrals in this form end up giving you the integral of secant cubed theta, and you need integration by parts to work on that, which was what I was trying to avoid. And then the one that didn't match ended up using it. So super annoying. But I was trying to give you integrals that at least would be manageable once you got to the substitution. That's my goal. I don't want it to be crazier than it has to be. I gave you a formula for the integral of secant theta that was given to you technically as part of Calc 1, but I gave it to you at the way beginning of 7.2. The integral of secant theta is ln secant theta plus tan theta. Sure, just pop a plus c on there. And then you're going to back substitute. We have a secant theta, we have a tangent theta, so you don't have to do anything super crazy here. Secant theta is, and if you want now to switch your radical back, if you like it better as x squared plus 2x plus 2, that's fine. I tend to put this in my answer if I don't have to have a definite integral. If it's a definite integral, it's easier to evaluate if it's written like this. That's all. If it's indefinite, I sometimes will just back substitute it to the original form. So sure, we'll do that. There's your secant theta. The tangent theta is x plus 1. And this is the second term of your answer. Now you just need to add those together. So we would say that the integral of x plus 3 over the square root of x squared plus 2x plus 2 dx is the result from the first integral, which is the square root of x squared plus 2x plus 2. Don't write the plus c twice, just write it once. And then the second integral. And again, each integral itself was not that hard. It was just understanding at the beginning how to split it up properly, which was all about what question 3 on your quiz was asking you about. Like, how would you split that up? So if you're making notes to yourself about what to look for, remember, if your trinomial is somewhere in the denominator and your numerator is 1 degree less, that's what should make you think about a U substitution. So start out your U substitution, see what you would need. And if it's exactly what you have, that probably won't happen because it's a Calc 1 integral. But it might happen in 7.9 if you're doing mixed practice. But it probably won't be exact. So split it up however you need to. If you need an x plus 1, fine, force it to be x plus 1. Then just take off the other 2 for your constant, split it into a separate integral, and then kind of go from there, see what needs to be done. So each one of these had just a lot of little things that needed to be done to make it come together. Okay, so that was 7-4. Any lingering thoughts, questions, anything like that on 7-4? Okay, so like I said, if you wanted to see 7, for example, 2 redone using a trig substitution, stick around for the office hour and we can do that. I did it using an inverse trig function. But either way, example 2, we had options. Example 6, we did not have the same options because of the radical. Okay. 7-5. So this is your last technique heavy section as far as integration is concerned. Now, 7-5, for the most part, is going to result in a bunch of small integrals that you're going to have a really easy time evaluating. It's just that you're going to have to rewrite your original to get to those little small integrals. And that's going to be the hard part, even though really it's something that is included in a college algebra textbook. At ECC, we don't cover partial fractions in college algebra. It's a section in the book that is not required and we skip over it because if you ever do need it, you're probably going to have to review it before you learn it anyway. Like, what if I would have been like, oh, you guys learned partial fractions in Algebra 2 or College Algebra, so we're just going to do this. We'd be like, wait, I don't remember that. That was like years ago. So it's probably for the best that it's not really covered in college algebra because they can't claim it as a prereq for you, which means I have to teach you how to do it, which is great for you. All right, 7-5. I always call it partial fractions. What's it officially called? Probably partial fractions, but my book is buried. So. Partial fractions, just the name of the section, sometimes people find scary just because integration of rational functions using partial fractions. Okay, fine. Integration of rational functions using partial fractions. Fine, that's officially what the section's called. I think because fractions always make people feel uneasy. So when I say that we're going to use partial fractions, maybe it makes you feel uneasy, but hopefully by Calc 2, you're not too upset about fractions in your life. The best way for me to show you how to do this is just to give you a bunch of examples where you'll find your partial fraction expansions, and you'll find that it's not very hard to do. It's another one of these algebra techniques that we're just going to employ here to evaluate integrals. So I'm going to give you an example, and I feel like you're going to see this and be like, all right, cool, fine, not that bad. And then some of these we're going to have to do using our calculators and some systems of equations. But that's no big deal. I'll just have to remind you how to do it. Okay, so I'm going to start out with a really, really basic example. So this is the integral of 2 divided by x squared minus 2x minus 8 dx. Okay, so the best part about this is that it's easy to recognize partial fraction integrals because either the denominator will already be factored or it's factorable. So you might want to make a note to self for these integrals, you'll know that you have partial fractions because either the denominator will be factored, either the denominator will be factored, or it will be factorable. That's usually how you're going to recognize partial fractions. Partial fractions, at least for using this method, that's probably going to be the easiest type of integral from chapter 7 for you to recognize. I mean, some of the parts, I guess, as long as you saw like, you know, two different functions being multiplied together, you kind of had an idea that you were in integration by parts. But other than that, some of these were really hard to recognize, like, what do I do? Where do I start? A lot of these, the denominator will already be factored. If it's not, see if it's factorable. If your denominator is factorable, use partial fractions. If your denominator is not factorable, then you're going to use a different method, like an inverse trig form if you can fit it in, which this one, you would probably be able to fit it just because of the constant in the numerator. You would just have to complete the square to make it fit. You can do that in the office hour if you'd like. We can always do all these using different methods. Or you can try to complete the square and do it using a trig substitution. You can do that also. But you're going to find that if you can use partial fractions, that's going to be an easier way to do the integral if you can use it. So I'm going to rewrite this by factoring the denominator. So I know that I can rewrite this as x minus 4 times x plus 2. And I know it seems very basic, but make sure that you factored this correctly, because that's the last thing you want to screw up, is maybe getting the signs wrong on this. I mean, it won't be a lot of points off on your test because I'll see it. And I'll just be like, oh, I wish they would have double checked this, but it happens. And it won't affect a whole lot, but your answer will be wrong. So just be careful to make sure that you factor this correctly. All right, so once you're there, you're going to rewrite your integrand. Take it out of the integral for a minute. You don't want to keep rewriting the integral. Take the whole thing. Now, if the 2 was already outside, that's fine. You can leave it outside. You'd have to just multiply it in later. But you can leave it in the numerator if you'd like. Now, note that there's nothing I can do with this the way it is. Right now, anyway. It's not a u substitution, because in order to be a u substitution, I would need a linear term in the numerator, which I don't have. I have a constant term, so I don't have du over u, so I can't even think about doing that. But what we're going to do is we're going to split this up so that we have one of these factors in each separate denominator. So what we need to do in order to do that is figure out what the numerators would have to be. So I'm going to split up the fraction as a sum of 2 fractions, such that one fraction has the denominator x minus 4, and the other fraction has the denominator x plus 2. You can't just split it up and assign the numerator however you want. You have to strategically determine what the numerator is going to be if you do that. Now, this is what we're going to do if you have linear factors in your denominator. We're going to talk about what happens if you have repeated linear factors, like if you had x minus 4 quantity squared. We're going to talk about what happens if you have quadratic factors, like x squared plus 2 instead of x plus 2. But for now, this is what we do when we have linear factors. All right, now you're going to rewrite this, and I'm going to show you the long form of this like one time, and then I think you guys will get used to doing this and you won't have a problem with it. But basically what I'm going to do is I'm going to multiply both sides of this equation by x minus 4 times x plus 4 to get rid of the fraction. So I'm going to, like I said, I'm going to show you the full way this time. I'm not going to show it every single time. Let's see if this one pops up. I'm gonna do this. Okay, so I'm gonna write here x minus 4, x plus 2 times twice over x minus 4, x plus 2. And then I'm going to do the same thing on the right-hand side. I'm going to multiply each term by the LCD to clear the fraction. Oh, my green isn't even showing up. Green. It's unfortunate. A times x minus 4. We're going to multiply by the LCD also. Plus b over x plus 2 times x minus 4 times x plus 2. You should have done a lot of this in algebra way back in the day. Your goal is to clear the fractions. Multiply by the LCD to clear the fractions. You're going to get very good at this. Students always do really well with these partial fractions problems, especially the basic ones like this. Okay, when you do that, you're going to cancel out your common factors. You're going to rewrite it. On the left-hand side, all you have left is this 2. And on the right-hand side, you have a times x plus 2, leave it factored, and then plus b times x minus 4. Now, you need to solve for a and b, so you're going to strategically choose values of x that will allow you to do so. This is an equation, so you're trying to figure out, well, what would a have to be if x was this quantity or if x was that quantity? So you're going to let x be, for instance, -2. If I let x be -2, then it's going to allow me to eliminate a, because -2 plus 2 is 0. And then the a term is going to go away, and I can solve for b. So if I let x be -2, I have 2 equals a times 0 plus b times -6. -2 minus 4 gives you -6. And this is 2 equals -6b. One big problem I see with students in this section is they see this and they automatically think -3. It's the number association. You see 2, you see a -6, and you say b equals -3. Be careful though. You're dividing both sides by -6, not by 2. So be careful to make sure that you actually write b as -1/3, not as 3. Now, if you'd like, you can substitute that in for b and then choose a value for x to solve for a. But if I were you, I would just, again, strategically choose a value, in this case, to eliminate b. So I would say let's let x be 4. And then you'll get 2 equals a times 4 plus 2 is 6. And then plus b times 0. You'll get 2 equals 6a, and then a equals +1/3. But the nice thing is, now you have rewritten your integrand, which you had no idea what to do with before, as 2 separate terms. And if you're wondering why is that a good thing, well, both of these terms are now going to be in the form of a constant over a linear term, which is du over u. So these are both going to be natural log forms. So we're going to say now that 2 divided by x minus 4, x plus 2 dx can be rewritten Zoom out a little bit again. Using this equivalence. So I can say that this is the integral of a over x minus 4, which is 1/3 over x minus 4, plus, and then b is negative 1/3 divided by x plus 2 dx. And we're going to rewrite this one more time to make it look a lot better. But officially, if you were doing a direct substitution based off of this definition, that's what it looks like. That's how we use partial fractions with linear factors, single linear factors. Does anyone have a question there? And some of these, you know, might just take a little practice. No big deal. Okay. So let's just rewrite these one more time. I'm going to pull the 1/3 out front. So I'll have 1/3 times the integral of 1 over x minus 4 dx minus 1/3 times the integral of 1 over x plus 2 dx. Now these integrals themselves are very straightforward, natural log forms. If you let u, I mean, you don't even have to do a u substitution here, but you could say, let's let u be x minus 4, du is dx. So you're just looking at du over u. That's your natural log. So you have 1/3 ln u, which is ln x minus 4. Don't forget your absolute value bars. Minus 1/3 ln absolute value x plus 2. Let's see. Since this is a very common type of problem, what you're going to often see is that the answers are simplified differently. This is fine. I'm fine with this. But what you might see is that if this is the same constant or if it has the same denominator, they'll pull that out. And then they'll use that definition for ln of ln A minus ln B being ln of A over B. So if you see that, that's where that comes from. I don't want you to be confused. So it'd be x minus 4 over x plus 2. And it, I mean, it just looks more concise. Either one is fine. If you feel like you're going to mess it up, just leave it like this. If your book has these, they're going to look like that. I mean, of course, your book has these, but if you're looking at the examples, they've probably left them like this. I'm going to show you one more of these that's super straightforward, just to sort of get you feeling comfortable with them. Add a slight twist. Questions on this one? Okay. So for example 2, same idea with a slight twist. So this will be the integral of, in the numerator, 2x cubed minus 4x squared minus x minus 3 divided by x squared minus 2x minus 3 dx. Now, some books in Calc 1 talk about integrals of this form, where the degree of the numerator is greater than the degree of the denominator. Some of them don't, and this book doesn't, and it's very frustrating because the first time you see that is, I believe, in this section. This is really, really, really important because what you could do is automatically factor the denominator and start doing your partial fractions, and then you'll be confused. You'll get to the end and be like, wait a second, I'm missing a term on my answer, or it's not accepting my answer. What's happening? Well, what happens is if you don't actually simplify this down so that you at least have the degree of the numerator being less than the degree of the denominator, you're going to lose terms on your answer. You can try to do that on your own time. I'm not going to go through and show you what it looks like, but I'm going to write you a note though, saying if the degree of the numerator of your rational integrand, remember rational means written in the form of a fraction, is greater than or equal to, so even if the degrees are the same, this applies, the degree of the denominator you must first simplify the integrand using long division. So in order to use partial fractions, you must have the degree of the numerator being less than the degree of the denominator for partial fractions. You must have the degree in the numerator being less than the degree in the denominator. You must. And you might want to highlight this because it has been a source of frustration for students in the past that they miss terms on their answer and they don't know why. Remember, the degree is just the highest power that you see on any one term. Okay, so what that means is you're going to need to divide this out first. We have done long division, I believe, in this class. Gosh, I don't remember if we have or not. Maybe it was in Calc 1 that we did long division. Oh well, we're doing it now. All right, we're going to take 2x cubed minus 4x squared minus x minus 3, and we're going to divide it by x squared minus 2x minus 3. We did this in Calc 1 when we were looking for slant asymptotes. That might have been the last time you used long division. I'm sorry if your Calc 1 teacher didn't teach you slant asymptotes. Again, though, this is another algebra technique. All right, you're going to take the first term in your dividend and divide it by the first term in your divisor. So 2x cubed divided by x squared just gives you 2x. 2x cubed divided by x squared is 2x. That's where that comes from. And then you multiply this 2x by all three terms in your divisor. So 2x times 2x squared is 2x cubed. Well, it better be. It's got to match up. That's where it came from. Then you're taking 2x times negative 2x to get negative 4x squared. Then you're getting 2x times negative 3 to get negative 6x. Remember, with long division, you always subtract. Some teachers show you just to change all the signs. I just do a minus and then put parentheses around it. You decide, but you're going to be subtracting. 2x cubed minus 2x cubed is 0x cubed. That should always happen for your first term. And then you have negative 4x squared minus negative 4x squared. So you have negative 4x squared plus 4x squared, which actually gives you 0x squared. Negative x minus negative 6x is negative x plus 6x, which is 5x. And then bring down any remaining terms that you have. Now, if you get to the point where what you have left over here at the bottom is a lower degree than what you have in your divisor, then you're done. And you can stop using long division, and you can just write this remaining portion as your remainder. If they're the same degree, you need to repeat the process over again. But right now, I'm just going to say that this is plus. I'm going to take my remainder, and I'm going to write it over my divisor. And that's how you perform polynomial long division. If you haven't seen it in a while, if you want to look it up on Khan Academy, polynomial long division. It's an algebra thing. And then you're going to rewrite your integrand as your quotient with the remainder. So you're taking your original and now you're rewriting it as the integral of 2x plus 5x minus 3 divided by x squared minus 2x minus 3 dx. If you have questions on long division, please do ask me in the office hour. Okay, now this we can integrate no problem. The other part of the integral is where the partial fractions come in. So we're doing 5x minus 3 divided by x squared minus 2x minus 3 dx. But this is going to be very similar. And if you want, we'll go ahead and factor it. We might as well. No use in just writing it one more time. This is going to be x minus 3 times x plus 1. Now, like I said, as long as you can factor it, it's going to be a partial fractions problem in your denominator. If you can't factor it, then you're going to try to complete the square and try to fit it into either an inverse trig form or a trig substitution. If it's factorable, partial fractions. So what we're going to do is we're going to go back to this integral in a minute. For now, we're going to focus on rewriting the integrand 5x minus 3 divided by x plus 3 times x minus 3 times x plus 1 as the sum of two fractions. So this is going to be a, and you can choose whatever variables you want. This is pretty standard to just use a and b. Sorry, this is a little bit off center there. Now, when you rewrite this, I'm not going to show you the whole like clear the fractions part again. You're going to get very used to doing this very quickly. You're going to keep the numerator from the right-hand side. And then if you want to even envision just kind of multiplying each term by your LCD, well, the x minus 3s will cancel in your first term, and then you'll have a times x plus 1, and then b, the x plus 1s will cancel in the second term, and you'll just have x minus 3 left over. And then you can apply the same rule. You're going to choose values of x that are going to cancel out a and b. So for instance, let x equal 3. Don't forget, you must also let it be equal to 3 on the left-hand side. So 15 minus 3 is 12. And then you would have a times 3 plus 1 is 4. And a is 3. And then you let x be -1 to eliminate b. -1 times 5 is -5, minus 3 is -8. The a would be gone in this case, you get 0. And then you get -4 being multiplied by b. -1 minus 3 is -4. And you would get b equals +2. And then you're just going to rewrite your integral as 2x plus a over x minus 3 and b over x plus 1. And now you have just 3 Calc 1 integrals all put together. These are both natural log forms, du over u, and then this one is just a standard power function. So increase the power by 1, divide by the new power, and you get x squared, and then plus 3 times the natural log of x minus 3, plus 2 times the natural log of x plus 1. Don't forget your absolute value bars. Plus c. I'll zoom that out for you. All right. Oh, and it's exactly 8:10. All the way. All right. If you guys have questions, stick around for the office hour. I'm probably just going to finish the 7.5 notes in the asynchronous lecture. I'll send it out at some point Friday. I don't know if I'm going to record it tonight or tomorrow night, one or the other, but it'll be up at some point by Friday at the latest. I'll finish partial fractions. I might go ahead and just put up the 7-9 homework depending on what's available so you can start on it, but I'm not going to have it due until right before the test because it is sort of going to be a culmination of all the techniques. Other than that, like I said, if you have questions, stick around. Otherwise, I hope you have a wonderful week, and I'll see you here next Wednesday for all the excitement that will continue in Calc 2.
Are we still on track for the test, or?
I don't know. Let me look.
And will you be putting up another review? Because that was helpful.
It's all of you.
Yes, but we do have several more sections.
Okay.
He's no. If you recall, he was the Meister.
Yeah, we are still on track for test 2 because we were supposed to I mean, I had 7-9 built in for like 3/4 of a day, and then I had started 8-1 before test 2. So we'll probably just do test 2 still on the 20th, and then we'll just wait to start 8-1 until the material for the following week.
Okay, just wanted to check.
Yeah. I mean, if that changes, of course, I'll let you know. But yeah, I'm still planning on, is that still 3 weeks? Yeah, 1, 2. That would still be 3 weeks from tonight. Seems like a long time. Maybe not to you. To me, it seems like, wow, we should have another test soon. Maybe I'm just anticipating all the pain of writing it and grading it. That's possible.
I'm anticipating the pain of taking it, so
Sorry.
I'm sure it's going to be better than the last one because I actually feel like I understand the material. Because as you were going through, I'm like, okay, I know what steps we're going to do next.
On your
So
way back, you could probably run
Good.
across.
Yeah, the second test in this class pretty much always goes better than the first. For most people, not for everybody, but in general, it goes better. All right. Anyone else questions?
Bodies in the house.
wow, everybody just hurry up and left.
Yeah, they were just waiting for the answer to your question. Yeah. stop my recording then. It's been taking forever.